Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. I see some more Live Labs folks drifting in. So it is my real pleasure to welcome Daniel Martinek here to Microsoft Research to talk to us about his thesis research. Daniel just finished his PhD at the Czech Technical University in Prague, which is where the ECCV conference was in, what was it, 2004? Right. And that's where I started taking some of the first photos that became PhotoSense later. Daniel was also, while he was a student, was participated in one of the teams that was working on one of these 3D reconstruction challenges that I had run for the ICCV conference. And most recently, since his graduation this summer, he started working for Microsoft. He's going to be joining the 3D team in Boulder at Vexel, working on commercial versions of PhotoSynth.
Thank you. So what you can see here is a result of automatic pipeline which we developed in Prague. So this presentation is my PhD defense. My thesis was led by Tomáš Pajdla and Mirko Navara at the beginning. It was all of this work was done at Center for Machine Perception at Czech Technical University in Prague. I will give a brief introduction into 3D reconstruction from multiple views, and I'll explain why it is challenging. I'll show some works of others and how they differ from our approach. After I formalize the problem, I will explain a few contributions of the thesis and some of them in more detail. And at the end, I would like to tell you about my new nice results. So we have some images at the input, which can be entirely unorganized. And the task is to calibrate the cameras and reconstruct what we can see in the images. We have quite general assumptions. We don't know the positions of the cameras and orientations. Once they are computed, it is quite easy to obtain reconstructions like this, if they are obtained accurately enough. And moreover, we don't know focal length, but we assume that other internal camera parameters are known, like image pixel. Principal point is in image center, and we have square pixel. So these kinds of images can be found, for example, on Flickr. This task is challenging because there can be many, like thousands or hundreds of thousands of images. This example has more than 2,000 images. There can be many occlusions, almost 100% like in this case. There can be strong perspective effects, so simple affine camera model cannot be used. There can be various connections with the cameras, like narrow or wide baseline images, and some images can be panoramas. Images can be either entirely unorganized or they can be in some sequences. And there is another challenge which is caused by repetitive structures and similar objects on the images. This causes that there can be many mismatches, which however satisfy the two-view geometry. So, for example, these 4 points happened to be quite similar to these 4 points, but they just accidentally lie on the corresponding epipolar lines. But these are different buildings. And the situation can be even worse. In this image pair, there is something like 1,000 inliers to some epipolar geometry, but there is no true match because these are different buildings. So this building lies on this side in this image. And of course, to obtain a consistent reconstruction of all the environment, such wrong geometries have to be rejected. So our pipeline starts with some images. We detect some regions of interest and match those similar ones. And using Ransack, we gain some two-view geometry, which can be viewed in 3D like this. And we simply try to combine somehow such pairwise reconstructions into a multi-view reconstruction. Once that's done, it's possible to identify some image pairs which are suitable for dense stereo. These are usually those with narrow baseline. So we can obtain such quite full dense maps, which disparity maps, which correspond to point clouds in space, and we simply merge these point clouds into such point cloud, which can be further approximated locally by Gaussians. And here we show just the principal planes of the Gaussians covered with texture. Here we have millions, tens of millions of points, and here we have just few hundreds of we call them fish scales. But one can go even further. This is the result of my master student, Radim Tilecek. He even found surfaces and used many depth maps so that it's more consistent and more complete. But all my studies were mainly about this step from two-view geometries to multi-view geometries, how to combine them. There's been a number of research groups which have dealt with this problem. On video sequences, there were projects, for example, at University of Graz, in Bexel. Real-time 3D reconstruction was introduced 2 years ago. For unorganized images, there were also some universities working on this theme, like in Oxford, Leuven, in Washington. And there are two ways how to approach the problem of unorganized images. First is the sequential, however, it is quite prone to local minima. And the other is factorization, which is, on the other hand, not robust to occlusions. I will speak about this later. And there is another approach, which I call batch approach, introduced by Gilbert, but it's usable for affine cameras only. So what we do? We wanted to develop some methods for automatic 3D reconstructions, which are general and can be applicable at the same way for both organized and unorganized images. We try to use all the data at the same time. We started our studies with factorization. However, as I said, there is a problem with occlusions, so it's applicable on few images only. Jacobs generalized factorization so that it can be used for occlusions too, but I'll speak on this later. There are some problems with that. And our methods, most of our methods which we developed, we call gluing of partial reconstructions. And this is not only robust to occlusions, but also to mismatches, as you will see. So we assume that we have some measurements in images. Here we use homogeneous coordinates because it's in the same way you can formalize the problem even for omnidirectional cameras. So we want to compute some point in space, again homogeneous coordinates, and camera, so that the point is projected by the camera into the image measurement up to some unknown depth. All the blue things here are unknown stuff. The only thing known is the image measurement. So it's possible to stack all such projection equations into one large equation. It's easy to obtain these lambdas, projective depths, from epipolar geometry. And if this matrix is complete, these crosses stand for missing elements, which are there namely due to occlusions. So if this matrix is complete, it's very easy to factorize it into a product of cameras and points using singular value decomposition. This is the result of Thomas in Canada, and many other people use this approach. However, if there is an occlusion, you cannot do this. So people tried to identify some large submatrix of this big matrix, do this factorization and then to extend the solution to other parts of the matrix. However, this approach is called imputation because you are filling some holes in this matrix. But the problem is that by filling, you introduce some error into this matrix, and this error comes just from few measurements. It's very local, and moreover, when you are trying to extend this solution, you are using this error again and again. So it's highly dependent on when you start, and so for difficult problems with many occlusions, this really doesn't work. There is another way people try to initialize these two matrices in random, and then use, for example, power factorization or damped Newton to alternate between filling and factorizing again. However, it doesn't work really for difficult data. So what we do, we just look into our pairwise reconstructions or into the camera, and we usually know the internal parameters, or we can estimate them based on pairwise image measurements. And so it's possible to decompose each camera into product of this internal parameter matrix, rotation and translation, and I will come back to this later. So we started our research with projective factorization. We combined perspective cameras and occlusions by Jacobs. Later we extended it for omnidirectional cameras. And then I was playing for a while with this famous dinosaur sequence, which has only 36 images. And it was really a problem. I couldn't do it using Jacobs' method. The problem with that method, it's a very nice and elegant way. Jacobs just takes 4 tuplets in that measurement matrix, and when there are missing elements, some big subspaces are generated. And he samples these 4 tuplets and intersects these subspaces. However, he does it in a way that he goes to complementary subspaces and he makes union then and goes back. This is the simple De Morgan rule. However, by going forth and back, he loses the connection with the image measurements. And when I found this, it was almost solved, because it was then sufficient to reformulate the problem in the original subspaces. And this is what we did, and it works amazingly well, even when everything is only in projective, without camera calibration. Then I studied further and came with a method which doesn't even need these projective depths. Then there was ICCV contest, and there were panoramas, and so I made some detection of these panoramas, and later on ICC 05, Frederick Hall's method appeared, which can just take absolute rotations, which I could already compute. I will show you later. And he casts a minimization problem using second order count programming, and so the translations and points can be estimated almost for free. And then I spent some time on making things more robust, which you will also see. So I think this was my biggest result, which I personally consider, and I will spend a few slides on these two remarkable results. So as I said, we start with some pairwise reconstructions. To make things simple, we forget about image data for now, and we have just the camera viewing directions. Well, and further, we forget about translation for a while. So we have just relative rotation. And we want to register such relative rotations into one coordinate frame or reference frame. And how we do it? So each such pair of viewing directions has to be somehow rotated so that it aligns well in the reference coordinate frame. And this can be very easily described using 3x3 rotation matrices. So you can see what's actually happening there. And we end up with such equations. which are linear. And this is a great thing. There is a lot of unknowns. You can see these matrices on the right side I call consistent rotations. These are the absolute rotation. This is what we want to estimate. And these matrices are mappings between the local coordinate frame of the pairwise reconstruction and the global coordinate frame. So it has a nice geometrical meaning. And moreover, it's very easy to solve. We use just eigenvalue solver. The problem has global minimum, which is nice. The problem is very sparse and very well conditioned because all the matrices there are orthonormal matrices. It's the nicest matrix. And it's also very fast. It's a fraction of a second, even if we have thousands of image pairs. And of course, the resulting matrices are not exactly rotations, but they are very close to them. So it's sufficient to project these matrices to the space of orthonormal matrices, or to use SVD, just to set all the singular values to 1. So this is the result of registering rotations into one coordinate frame. You can see that, for example, this camera number 22 is there several times, because still the translations have not been registered yet. But after calling Carl's method, you can see that the problem is almost solved. Here we have reprojection errors. The mean error is below 1 pixel and the maximum is below 20 pixels. You may say it's quite a lot. I will arrive with a new method which doesn't have such problem. But still, on a linear method, it's quite a good result, and it's very, very, very fast. Rotations are in fraction of second, and translations are in a few seconds.
Daniel, if I remember some of the techniques, I don't remember if David Nister was one of the people who worked on this. When you know the rotations, there are solutions for the translations, but points far away, points near infinity, often bias to make those things not work very well. Is that correct? Points at infinity have problems? Or is it only if you try to do sort of a linear version of the problem?
No, this is second order programming.
Second order programming takes care of that because it's
You're
divided by the
referring
depth.
to Carsten-Walder's method, where you have to assume points at infinity to get the homography, which is not. There are other methods that don't do that.
Okay.
I have met no problem with this method, except that it relies on point measurements.
Okay, so it doesn't matter. You're also seeing points at infinity. You don't have to throw those away. Okay.
And this is the result after final bundle adjustment. And you can see that nothing really changed, which shows that we are very close to the local minimum. Of course, we don't guarantee global minimum. The problem is non-convex, so it's but our worst reprojection error is now below 2 pixels, which is, I think, a nice solution. And also, you could see that there is a big point cloud which moved, and it's due to points visible in these two images, which are in fact a panorama. It's just a close-up. And this really didn't matter in the method, if there were panoramas or not. And even it doesn't matter if the points are on some dominant planes. This is really robust to all these things. This is another example of almost 300 images from a mountain scene. This is another shot. This is an example of the two images. So a few words to mismatch identification. As I said, in this image pair, Ransack on epipolar geometry identifies these mismatches as inliers. How to...
Can I ask a question about the previous approach? So you assume that you have enough rotations estimated pairwise that you can figure out the globally consistent set of rotations. When you have very wide field of view cameras, you can often reliably estimate rotations. As your field of view gets narrower, isn't there sort of an ambiguity between the rotation and the translation that makes it hard to get good pairwise estimates?
Yes. So, for example, these two cameras, translation, in fact, is not determined there at all.
Right, those two cameras, because they were taken from the same point of view. I'm saying if you basically, if instead of taking out your 35 millimeter camera or your point and shoot, and the way all these cameras power up is they're in wide angle mode, if you force yourself to shoot a world with a 100 millimeter lens, with your pairwise rotation estimates just basically be poorly conditioned, or if you were flying from an airplane that was shooting aerial photos. In other words, if the images are less perspective, can you estimate rotations accurately pairwise?
Well, I have not worked with such a camera. Yeah, a strong assumption of this approach is that these relative orientations are quite well estimated. But it works somehow even if there is error of 100 degrees, which I have seen this on the mountain scene sequence.
So maybe because you're doing a big least squares, those errors cancel each other.
It's a big least squares, and each of the terms has almost equal weight. So even if one is really off, and there's enough others, they can make it better.
Okay.
Yeah, but yeah. So I've made an observation that if there is a mismatch, it's usually far from other images. Far from other point correspondences, and there is also both in image and both in depth. So I made a very simple heuristic that I fitted all my measurements in image multiplied by those depths. I fitted a Gaussian to them and removed everything which is on the boundary of the 25% of the points which are furthest from the Gaussian center. And it turned out that all such bad guys disappear this way. Well, there is more comments on this in the paper or in the thesis. I know it's heuristic, well, but on the other hand, if you have only such two images, I cannot really. This is really difficult to find out which points are mismatches and which are not, if you don't have any other information, some prior.
But if you're weighting points by depth, these scenes happen to have, they're closely cropped so you don't see a lot of the background, right? But if you had shots where there was just a lot, you saw the mountains in the distance and things like that, and there was a dominant object, then, things far away, if you really are weighting them by depth, will really dominate.
Yeah, of course, you have to re-weight all your depth so that the mean depth is 1 or something like that. It's kind of a projective approach. It works even if your cameras are not calibrated. So it's very general. It works for omnidirectional cameras, and especially on that mountain scene with those kilometer distant objects, it works.
Okay, so it's done more in a projective framework. Right?
Yes.
Basically, if you take the homogeneous vectors, turn them into one norm, then it's meaningful to talk about the center of mass.
Yes, exactly. Yes. Of course, by this way, it happens that I remove some good data too, but I don't mind. I have enough data, and 75 data is still there. And this image pair it had the largest amount of inliers, 25%. I haven't met any other data like that. So these are the inliers which survived this test. And by removing these mismatches, our reprojection error after the translation estimation went down from 100 pixels to 22. But we can do even better. It's possible to pick out only 4 points among these our inlier estimates, so that they represent the pairwise geometry almost as well as all these points. Well, and this is very simple, because the camera matrix has just 4 columns, which means that when it projects the points, only a subspace of dimension 4 is generated. So the only thing you need is 4 linearly independent columns. Well, and of course the question is how to pick these different or independent points. We use the same technique as for identifying mismatches. So we fit a Gaussian here, pick one point which is most different from the others, most distant from the center of the mass, and repeat this 3 times on a three-dimensional subspace and two-dimensional subspace, because once we have one point, we can care just from the remaining data, which is not explained in this dimension. And by this, we gained speed up factor 2000. Well, so instead of spending 4 hours on translation estimation using those tens of thousands of points, we use just few hundreds of points, and it's in few seconds, with really similar results in terms of half a pixel or so.
This is for applying Call's technique, right?
Yes.
For the translation. But what if the points you pick aren't present in other images? I mean, you need to find points that are also there. Or that's right, Call's technique is only pairwise, right?
Yes. Everything, so far, everything was just pairwise, which means that you can have really bad data. It works even if there is no point visible in 3 images. Well.
Are you doing it because the second order cone program is too slow?
Yes, exactly. It's very slow.
Well, there's something there. My intuition is that you need throughway overlaps for a reconstruction to be consistent, right? Or is it because if there's enough sort of things looking at each other from different views that there's only one sort of consistent solution? Right? If you walk down the street and you never see any point in more than 2 images, it's going to be hard to figure out exactly how fast you're walking.
Yes, of course.
Right. But if
There
you're
is
all looking at the same dinosaur, then you don't necessarily need to see a point in 3 images.
Yes, if your camera moves along a straight path, and you are using only pairwise data, then of course you cannot estimate the scales.
Right.
This never happened in my data sets. Well, and of course you can plug the points in 3 images, and I use them in any number of images in the final bundle adjustment. But it's better to use them as soon as possible, as early as possible in the optimization. And in my new stuff, they are there from the very beginning. So this is the scene which you've seen at the beginning, and I can show you the result of photosynth. Oh no, not this one. So it's split into 3 components. Well, which doesn't say anything about multiview reconstruction, but it says just that I have better matching so far. So this is another example. There were several such epipolar geometries which are wrong. You can see that this window is slightly rotated here, or it's entirely another window. Just it happened that all of these tiles on the roof just look similar, so it's difficult really to find if it's true or not. But we used all the pairwise reconstructions, and we obtained maximum error more than 100 pixels. And we used a simple technique. We identified the pairwise reconstruction in which the reprojection errors were the highest, and remove these, and repeated that few times. We arrived to a reprojection error of 7 pixels here, and you can see that the reconstruction is really consistent. The surfaces visible by different cameras fluently go one into another. So this is the most difficult example. Here you can see that we kept removing epipolar geometries, but then it started to oscillate at about 30 pixels, and I think this is really difficult scene, and I think the method for identifying non-existent epipolar geometries has to be more sophisticated than this simple relying on that least squares are robust enough if you have good conditioning. So I've spent some time on this research, but then then my attention was again given to enhancing precision. So this is another example of that seen with more than 2,000 images. It was a paper model made a few hundred years ago. It's a part of 6,000 building model of Prague. It was a very nice project, however it was cancelled, so this is the only data which I had from it. This linear technique worked on it the same way as on the other scenes, so I'm pretty sure that it would work on even 10,000s of images and maybe more. But unfortunately I didn't have any larger data yet. And moreover, I could not reconstruct the dense reconstruction using my software because I didn't want to spend time by rewriting it. And the depth maps just didn't fit into 16 gigabytes of memory. And then the project was cancelled. So I've shown some techniques on projective and metric gluing, which we developed, which are quite accurate and relatively fast and robust. Of course, I had to write all the software, or some of the software was from others. But for example, I found some heuristics for speeding up matching image pairs. I made some work on relative pose estimation when the focal lengths are entirely unknown. I worked also on line reconstruction. The software is part of multi-camera self-calibration package, which is widely used in the world. And I wonder that people still use it because my technique in that package is from it's 6 years old, and there was never need to replace it by the new, more robust techniques. The software was sold to a Canadian company last year, and it's used not only by people at our university but by another university too. It was well accepted by vision community. We ended up second at the ICCV05 vision contest. We published it in quite a few papers. Yeah, so this is everything from my from the stuff which I published in my thesis, but there is some new stuff too. We've touched some problems there already, and I think I identified 2 problems. First is that the rotation representation is not good in that linear estimate. Well, because what I gain is only an approximate rotations, not rotations, because rotations satisfy some nonlinear constraints, and thanks to that, some errors can be inherited from some pairwise reconstructions, and translations can produce large errors like in 50 or 100 pixels, which may sometimes converge to nice solution, but sometimes not, and I really didn't like to I wanted to make it more robust. So my new approach has no approximation, no linear estimation of absolute rotations like at once. It doesn't even use second order programming. It simply takes the pairwise reconstructions which we have and tries to modify them slightly so they are more consistent with each other. And when they are consistent, the problem is solved. Because then it's very simple to chain these consistent rotations, consistent reconstructions which are consistent both in rotation, in translation, and scale too. And this solution has a very nice properties because we have low reprojection errors during the whole optimization process. Well, each of these pairwise reconstructions has some image points. I use 4 points, which you've seen, but you can use any number of points you want. And so on these pairwise reconstructions, the problem is solved. However, it's inconsistent with the other reconstructions. So the only thing which is needed is to add some penalty term, which penalizes some constraints in which are on top of these pairwise reconstructions, and this is something which has to be solved. So I think that by keeping these reconstructions consistent with the data all the time within reprojection error of, let's say, 5 or 10 pixels, we can avoid some really bad local minima. So we get better accuracy. It's all well scalable too. I've tested that on 300 views only, but as the old stuff worked on thousands, I can try it. I may try it on tens of thousands or even more. and some things which are needed in the project. I work on geosynths now, and they need some stuff like adding some priors to the cameras. I think this is really natural way how to do it. We have these pairwise reconstructions, and if you have some idea of how the cameras are rotated or translated, I think it is very easy to add it to them as the data terms. Well, so this is not finished, so I can show you some equations in my paper. So this is pose, relative pose between images, between views I and j. This is relative rotation, and this is relative translation. Well, and this is composed relative pose, which is just chain of such relative poses. So, for example, if we have 3 images, we just chain these two and arrive with something like this. So this is very simple. And I want my relative pose to be consistent, to be the same as some chain of relative poses via some other relative, via some cycle, either triangle or cycle of larger length. And so here I have some theorem that this what I want is something which has to be satisfied in the final reconstruction. And so the question is how to enforce it. Well, it's quite simple to see that this rotation should be the same as the composed rotation, just by these relative rotations are just multiplied. It's slightly more complicated with translations, but if you wanted to minimize as in the penalty term, if you want to minimize the difference between the left and the right hand side of this equation, there is a problem, and it is the scale in this translation, thanks to which these terms have different weights than these terms. So it turned out that it's much better to minimize the difference in essential matrices. This is one way. Or another way is to minimize reprojection error using on composed camera matrices, which is the camera matrix of image J. These are internal parameters, and instead of using HJI, I use the composed relative rotation. So we arrive at the end to 2 formulations. One is using these essential matrices, and one is using the reprojection errors. So this first term is the standard bundle adjustment. This is just the reprojection error. Well, the reprojection error is defined. You throw into it some image points, image correspondences, some cameras. This is a pair of cameras. Well, one of the cameras is fixed, and the other is represented by relative rotation and translation, and this is my points, either 4 or more, and this relative rotation. These are just the squares of the errors, and this sum says that I sum over all images in that pairwise reconstruction and or columns or points, and I do this I sum over all pairwise reconstructions. So this is simple, and this is the term which is my penalty function, which should be 0 at the end. And of course at the beginning it is not usually, because Ransack doesn't know about the other data. It relies on that which is in 2 images. So this term is non-zero, and it turned out that it is sufficient to minimize its weight, just to initialize the weight just by to 1,001, sorry, 1,000ths. No. This weight is 1,000 times smaller than 1.
You're doing the continuation method where the right-hand term initially is small. And then
yes, exactly. And I gradually want it to be more consistent. Yeah. But if I push too much, it's possible that this term gets higher projection errors, and this is what I don't want. So I have to be quite careful about this. And another possibility is to minimize exactly the reprojection error, but on the composed camera, well, which has instead of the relative rotation, it has the composed rotation. So this may be closer to, and also there is also some weight. And that's all. The only problem is how to minimize this function, and it turns out that it's possible to either have one weight, which is shared by all these triplets, or how many how long cycles you want to have, and how to not to push too much, and it works very well. I can show you some.
So are you going to say a little bit later about having per triangle weights, because there's an index there, right? So it suggests that you have a different weight for each t.
Yeah, it can be different. It's up to you. I have it here with different indices because it's possible to solve this problem locally only. Imagine we have some network of our relative well, these are, each line is an epipolar geometry. Etc. And let's say in this triangle that penalty term is the highest. And it's possible to just take these few neighboring triangles. So this is this one, yeah, and that's it. And few more triangles which neighbor to these, which are this one and this one, and to optimize only this part. These three epipolar geometries, or these other, can be modified to rotations and translations, but these are kept fixed. Okay. Which means that we lower some residuals here, right, but stay consistent with the rest of the world.
Oh, so you use the omega ijk to basically freeze parts of the reconstruction and do subsets.
Yes.
Okay.
Yes.
So why don't you finish your talk? I have a suggestion.
Yeah, that's all. It's not finished well, so I couldn't finish the slides.
Some results?
Yes, so sorry, some results, yes. So I can show you the result of photosynth again. So you can see that there is really some, I don't know if you can see it. There is some problem that some of the walls in this right hand side are not perpendicular or parallel with each other. You know? So in my method, this is, I would say this is correct.
Your method produces nicer looking colors.
Thank you. This is 1/10 of all dense points generated by Dense-Stereo in our pipeline. And these dense points have the nice property that they can really reveal the inconsistency, which I need, because I'm trying to develop algorithms which are highly accurate. And here you can see that this part of the roof is there twice, maybe more times. This is especially the data which I want to work on, because yeah, there are not many images around. There is another image set of this with this house, but it's from summer. That's why there is more features on the ground, and it's very nicely reconstructed on the internet. But this one is winter, and so on this scene I really realized that I have to use triplet-wise correspondences, and I'm using using them in this framework, it's really easy to express triplet-wise reconstructions using relative rotation and orientation only. And it is really equivalent to having triplet-wise partial reconstructions. This is something which we discussed in last couple of days.
So how important do you think it is to get the matches versus, so kind of the experience that I've had, so I've looked at the summer data set of that a lot, and if the matcher does not close the loop, clearly the optimization can't close the loop. So if you miss a match, typically what was happening in some of those data sets is that it would miss, we were using SIF style matches, so it just won't do that. You're using a more affine variant style of matching. And so the general thing that we've seen is that if we get the matches, we typically don't have too much problem with the loop closing. And so if the matcher closed that loop, which we were able to do when we kind of raised the resolution we were running at, then the optimization tended to have no problem closing that.
Yeah, if I don't have the loop closed, I cannot do anything with it. And if I have the data and it's weakly conditioned, I have just in some of my data sets I have just 8 inliers, and I'm happy of them, and I can make use of them, and I can really make it consistent on all of these points. So of course, the more matches you have, it's better. But I don't think without the long loops you cannot expect that this would be somehow better. This is just a standard bundle adjustment. Nothing more. Maybe I avoid some local minima, but I need the data too.
So in your work and in Forcent, they both use the same matches?
No. Yes, of course. That's another point. Yeah, the pipelines are different. We have many nice features like Mikolajczyks and many types of MSERs, and we use local affine frames and DCT coefficients for the descriptors and SIFT features too. I found out on the mountain scene that SIFT features are not really good, because some of the pairwise reconstructions have as low as 2% of inliers, because everything is stone. Well, so MSERs with local affine frames work much better than SIFTs. That's why for identifying really epipolar geometries, I use MSERs only and Mikolajczyks, and if there are some, I use SIFTs for densifying the data, which may help, but I don't rely on SIFTs.
Clarify, are you saying that you take multiple subsets of views, so you have sort of multiple bundles, and that's what's on the left, the cross function in 14, and then you add the consistence terms between them, and then you sort of pump up omega until
Yes.
it goes to infinity, then they have to be consistent. You can just roll them out and be consistent up to numerical positions.
Yeah, I hoped originally that there could be just one weight, which is shared by all the all the loops, and I thought, okay, but by just raising it by small amounts, I must arrive to something which is really consistent. But unfortunately, this is not true. I think it's because this is just least squares, and it has many local minima. So then I arrived with this local method, which just tries to repair the highest residuals. So I have like graph like this, where here I have triangles, and at the beginning they all have large residuals. Well, it can be somehow like this. And so I identify the triangle which has the highest residual, like this one, and do something on it. 3 steps of bundle adjustment, so that the residual gets, I don't know, to 5 50% or 70%, how much you want to be fast. And together with that, some neighboring residuals go down too. So now I improved the consistency between the data. And now I identify again and improve it. And at the end I have it like this. And so first I start with these essential closure constraints, because they are applicable even when your points are behind the composed cameras, because this can happen. If your relative rotations, they can have error like 100 degrees. They can be 100 degrees away. And it's very easy that some of the points are just behind the camera. That's why you cannot use this formulation, because it's a nonsense. If the point is not in front of camera, it's nonsense. That's why first I do few steps using this part, and then I switch to this, which really is reprojection error. That's nothing else. And at the end, of course, it's not entirely consistent due to noise, due to image noise. So I start with some triangle, make the 3D reconstruction of it, and add some other triangles. And usually I don't have to bundle again. Usually everything is below 2 pixels. So only when it grows to, let's say, 5 or 10 pixels, usually not more, unless only sometimes when there are panoramas, and then the translations. Or I don't know exactly. So I can just grow the solution, and this is something like your seed, how it's called, growing. Yeah, but now I have everything pre-registered very, very tightly. So
what's your gut feeling if we did this by a seed and grow and only enforced consistency on the new loops that are created every time you add a view? Would this do as well as what you have?
I've tried to do something similar. I've tried to grow like 2 components which somehow overlap somewhere, or maybe more components, and tried to enforce similar constraints like this on these sharing cameras. Well, there may be other constraints. I haven't tried much of that, but it turned out that once you put this big set of cameras into one consistent system, and they are very, very tight, and it's really difficult to do anything with them. So it's much better. It seems to me that it's much better to have everything just pairwise, make everything consistent and just grow, than doing this growing here. I don't know. I really had problems with this. It was just inconsistent, and it just didn't want to be together on these overlapping cameras, which is the same case as you told, which if you have, if you have this, no, this is a similar case.
That's the loop closure.
Yes, I'm really skeptical. If this is in one rigid frame, and you try to do something here.
No, I'm talking about bumping the whole thing, but with an extra pull turn. Say this is a new loop, so I'm going to really pay attention to pulling that together.
Yeah, I know, but
your triangle example doesn't have a loop in it. What if you actually drew a loop? Wouldn't you run into the same problem?
Oh yeah, it has many loops. I have many loops in my data.
So as you're going along, you're kind of saying, well, I'm just going to keep adding things in. At some point, you might close the loop, because you're starting with something. After you've run this algorithm, when you want to pull out a final consistent geometry, right, camera set of matrices, you say start at a triangle and kind of walk out and don't rebundle unless your reprojection error gets too big.
Yes, exactly.
But you're going to keep doing that. You didn't tell us what happens when the 2 ends meet.
Yeah, when I'm doing this, so let's say I make this into one consistent frame, one rigid frame, but I keep the connections with the rest of the world, which is still pairwise. So even if I add something, and maybe reprojection errors can grow to 10 pixels here, but I bundle again with everything others, and this repairs a bit. So even if the loop should be somewhere else, I get there. Because, yeah, I'm growing here, but this shouldn't be here, it should be here.
Final triangle.
Hmm?
Right, so you're guaranteeing that everything is globally consistent in the part that you're growing out.
Yes.
And that all of the relative orientations locally are consistent.
Yes.
But
Even
at some point, when you add that last triangle
No.
that generates the cycle,
okay, I can
you're going to have to reconcile it, right?
this is difficult to to draw. So I have something.
There's nothing that guarantees that when you add in
No,
the final
there is.
that they're absolutely consistent.
So let's say I grew to some point like this, and still here I have some triangles which are not in that big reference frame. So I continue growing, and now it turns out that it should be like this. Well, that this camera should not be here, but rather here. But because it's connected to the pairwise reconstructions, the rest has to do some changes.
I think I get what he's saying, which is that as you freeze certain cameras to make them into absolute global coordinates, you still keep re-optimizing the other pairwise relations. So if there is a loop closure, the things that aren't frozen yet are going to keep re-optimizing themselves. So it's like, you know how you want to pull a tire onto a rim when you're fixing a bicycle tire? You know, sort of other parts that aren't quite over the rim yet have to start moving so the whole thing works. So I'm guessing that maybe what Daniel is saying is that even if you're putting final numbers on certain camera poses because you want those global numbers, the ones that are still not finalized participate in the optimization, so they're pulling you in towards a sort of a closure.
Yeah, but it's not exactly like a bike tire because it's just these relative. So you're only imposing these relative constraints locally on the part that's not on the rim.
Yeah.
Everything can move, and all these relative.
Well, they're distributing the remaining error, but
there's nothing that guarantees that these things sum up to some absolute correct path.
I mean, the things that are frozen, if you're doing a freezing strategy, they're frozen. You'll never get to re-optimize them based on the bundling. You have to hope the pairwise stuff distributed with the error enough.
No, you're re-optimizing. You're not freezing the cameras.
Oh, you
No.
rebundle some
You're
parts.
just,
Okay.
He's just converting them from relative
Right.
transformations to absolute.
Yes.
Right. Okay.
And rebundling them all.
Yes.
Right, so
Right. Yep.
you have some subset that is absolute,
Yep.
and so they're globally consistent with
Yep.
each other in the reprojection error. And then you have a remaining subset that is relative,
That's right.
and they're all chained together locally.
Yeah.
But if you traverse this chain, there's no guarantee that the path between the two is going to achieve the same transformation as if you go globally around the big loop.
Hey, look, I tried to draw it here. I started, my data was somewhere here. It doesn't.
If you chain together the path, you're not going to end up at the same position.
I chain it one by one triangle, let's say. Well, I do it by more triangles so to be fast. But so I change this triangle to this, and this is magenta here. This changed a bit, and then I going here, and this changed a bit too. So I'm enforcing that it has to be changed. That no inconsistent.
The global ones are being rebundled, and the remaining ones, which are local, are also being rebundled as part of that, right?
Right, but the path through the local does not give you the same. If you were to propagate the camera position by
Right.
chaining together the
Yes.
relative ones,
That's right.
it's not going to give you the same camera position.
Of course not, but only just up to 2 pixel reprojection error. And if you chain something which is connected within 2 pixel reprojection error, of course, if the chain has 100 elements, then you can really fly away. But if there is just a few of them, you cannot get really far. And I'm really, as I continue, I have less and less chains. So at the end, I have something which is consistent with this entirely, between this and this, and between these 2 or 1 element, it's consistent within 2 pixels only. So I cannot really be somewhere
So
else.
another option would be to, you don't have to grow it out from one spot. You would kind of take subregions and grow them all simultaneously.
Yeah, this is what I tried. I tried to grow all triangles at the same time, So I've got a lot of big components which are entirely overlapping each other, and sometimes some components follow some other components, so the data cancel. Yes, it works too, well, but it's too much computation. I really didn't see any advantage of this.
I just was interested, you mentioned speed up, but do you have any metric that this gives over other methods?
I think that speed up was for second order programming, which is not used here. This is just standard bundle adjustment with some few terms, either algebraic or really a projection error.
And bundle adjustment using relative poses instead of absolute poses, right?
Yes.
Okay.
And then a mixture of both at the final stage.
So I understand correctly, it's multiple bundles to happen with linking constraints between something to stay consistent. So you can start calling it that without ever instantiating the global coordinate system until much later.
You are proposing that I could.
Multiple gauges in this bundle adjustment, right? And then you link the gauges with these relative.
I don't exactly understand the gauges stuff. In my case,
Yeah, that's what.
yeah,
It's
I
all
have
local, right?
each.
So there is some combinatorial number of gauges if you want to think of it that way.
Each ij partial reconstruction is represented by zero rotation and translation for the first camera, and by relative rotation and translation of that image pair. So this is these are all my parameters which I have, and of course I have some points associated with those few points, and this is my reprojection error. I call it this way. So this is my data term, and this is already consistent at the beginning. It's below 2 pixels, and as it has large weight relative to the penalty function, it stays consistent.
I think I understand, but I wouldn't call this that bundle adjustment anymore.
Okay. Thanks.
Yeah, bundle adjustment means a lot. That's right. I guess it means adjusting all of the global parameters, but it's a nonlinear optimization over an over-complete set of parameters, which is the local poses, the relative poses. Right? And what would you say is the biggest advantage of this over running the full bundle over, if you had the same, in other words, you're solving an optimization in a larger number of parameters. You could also be solving it in the global parameters right from the beginning. What's the advantage of relaxing on local parameters?
It is exactly the same argument as here, because once it's in a global frame,
right.
Less parameters,
Right.
you cannot change much without introducing large errors on some of your data.
So everything's kind of stiffer in some way?
Yes.
Well, it's looser.
Well, I think
Sorry, the bundle is the classic method is stiffer, and this one is looser.
Yes.
The new one is looser. The
Yeah,
relative.
well, so the part that is an absolute coordinates,
Right.
that's exactly like a standard bundle. So
Right.
all the measurements are the same, and it looks just like a standard bundle.
Right.
But then there are all these other measurements which don't have to satisfy exactly the constraint
Right.
of chaining together into an
Right.
absolute coordinate system. And
Right.
So in
And
that
so
sense, you can kind of softly impose.
It's softer, so maybe it converges faster than with a standard
Or
bundle
maybe more
adjustment.
likely to
You have to
converge.
kind of knock all the points and all the cameras together, right, to move.
I don't fully buy the argument, but you could probably have a four-person
Okay.
discussion.
Yeah, all right.
That's fine.
Any other questions? Okay, thanks a lot then.
Thank you.